Hello, my name is Vince Jodwin. I'm a group leader here at Oak Ridge National Laboratory's Nuclear Security Modeling Group, and I'll be giving a lecture today on post-detonation nuclear forensics. So this is very right in the time scale of things, right of the boom, as they say sometimes. And I'd like to thank and acknowledge the sponsor of this videotape, the NGSI program, as well as all the staff members in my group who've done some of the work that I'll be sharing throughout the presentation. A little bit about my background is I'm a retired Air Force officer that came to Oak Ridge in 2005 and started a fallout research and development program back then. And in about 2008, it transitioned into nuclear forensics, post-detonation nuclear forensics. So the goal of the presentation is to give you some background in post-detonation nuclear forensics to interest new students and researchers into this field. I'm going to use some historic videos to explain debris collection and analysis, as well as a modern scenario to motivate the science. And then I'll review some recent fallout modeling and simulation research done here in support of National Technical Nuclear Forensics, NTNF, ground collections. So as you can imagine, post-detonation nuclear forensics requires a broad set of knowledge, including the physical, chemical, and radiological properties of fallout, nuclear data, fission, activation products, radiochemistry, nuclear weapons effects, thermodynamics, health physics, radiation detection and measurement, meteorology, computer science. You can name just about anything on this list. It has a role to bring into the post-detonation forensics. So what I'd like to start with is a review of where we last detonated nuclear weapons in the U.S. in 1962. Although atmospheric testing went on by some nations until 1980, the last ones the U.S. had for testing were over 50 years ago. So I have 3 short videos here that talk about those that occurred in July of '62. Let me try.
By this time, the light Davy Crockett, which had been displacing in the rear of the Advance, was in position to begin adjustment of fire on the target of opportunity. The heavy system was required to alter its route of displacement because of radiation intensities, and was therefore somewhat delayed going into position. Nevertheless, within 11 minutes of the time Objective 1 was taken, the heavy system was in position and firing its final adjusting round.
And so the first 2 videos here are both what we call Little Feller 1 and Little Feller 2, the names of the tests.
Set for a low height of burst, it detonated perfectly, releasing its lethal radiation. Like any other nuclear weapon, the Davy Crockett gives off 3 basic effects: heat, blast, and nuclear radiation. By far, the most significant effect is its deadly initial nuclear radiation.
So these were all low-yield shots. The other 2 are Johnny Boy and Small Boy.
Our next major information on low-yield nuclear cratering effects comes from 2 shots in the Nougat-Storax test series in 1962. Also at the Nevada test site. One of them, Johnny Boy, was a 1/2 kiloton shot detonated about 1 foot below ground level. Technically still classed as a surface shot, this shallow underground burst produced a visible fireball flash, but no base surge materialized. The cloud rose to 7,000 feet, slightly higher than the clouds from either of the jangle shots. But the difference was probably not significant, since meteorological factors also affect the cloud height.
So these are all low-yield shots, low yield being defined as less than 20 kilotons, which is sort of the nominal yield of a first-generation weapon. And the last one I don't have a video for is Small Boy, also detonated in July of '62. So what is post-detonation nuclear forensics? In a nutshell, it's after an event, can you tell the difference between a little boy and a fat man? Little boy being the uranium gun type device, which Oak Ridge had some contribution to, and Fat Man being a plutonium implosion device, different designs, different materials, and you want to be able to go in after an event, take the fallout, and be able to determine some information about the event to hopefully tell you who the perpetrator was in the event. So nuclear forensics is a technical field that feeds into sort of the law enforcement and intelligence aspects, or the policy side, which is attribution. And they used to just call it nuclear attribution, but then they divided it up to make sure that the scientists knew they weren't supposed to be meddling in the law enforcement piece, and the law enforcement side knowing that they needed to rely on the technical nuclear forensics data that could be provided. So this is the continuum that I was talking about before, where we're on the very right side of this timeline. You've heard previous talks or lectures on some of these other areas, and we're going to be focusing on what happens after the detonation. So how is the U.S. government, National Technical Nuclear Forensics, organized today? Well, you can see it's an interagency endeavor with different agencies taking a different focus area. So you have the Department of Defense is primarily interested in post-det events, which is the area we're talking about today, whereas the FBI, the DHS, and the DOE also have some contribution to that as well, not to mention the ODNI, the Office of Defense, or the Nuclear Intelligence, National Intelligence, Cabinet Office. So all these groups come together with the foundation of the national labs, as this chart shows, supporting that nuclear forensics expertise. So I said up front that I wanted to try and motivate this with a modern scenario. So there aren't a lot of videos out there that talk about post-det nuclear forensics, but there is, of course, one, The Sum of All Fears, a movie that came out in 2001, but the book of which was written in 1990, early 1990s. So it's amazing that the book talks about all these areas decades before 9/11, or a decade before 9/11, and the movie, of course, came out right around the same time as 9/11. So it's going to go through a lot of things, and I want you to be watching this video and listening to think of some of the technical nuclear forensics questions that are being asked in the video, so that perhaps we can have that discussion during our later question and answer session in April. So this is a short video. It's been edited for content and time and formatted to fit your screen. Whoop. And if I only knew how to run this demonstration. Let's try this.
It's Ryan!
Jack, where are you?
I don't know, somewhere outside Baltimore.
Listen, Cabot got the president out.
Where's the president now?
They're taking him airborne. He's on NAOC.
Why?
They think it might be the Russians.
It wasn't the Russians. I gotta talk to Cabot. Can you pass me through to the plane?
Cabot's not on the plane. We don't know where he is. We just know he's not there. Can you call back in about an hour?
We don't have an hour. The Fowler's gonna want to show how tough he is. He's gonna hit back now. Listen to me. We have to prove that it wasn't the Russians before he's convinced it is.
Well, can you get back to Langley?
No, there's no time. There must be a command post on site. The radiation assessment team, where are they?
Stabler Tunnels, south of the city. Jack, listen, the prevailing winds are blowing the fallout to the east and the north. As long as you stay south, you're okay.
The ash isn't radioactive, and the prevailing winds are blowing the fallout to sea.
Captain. Jack Ryan, CIA?
Lord Shiro, you need to wait outside with everybody else.
Oh, I don't think so. I need to know everything you know about the bomb.
Look, pal, we're collecting samples, then we have to analyze the debris. So take a number, get in line, and we'll have the report out tomorrow.
Captain, I don't have time for this. I need to know where this bomb came from. I will settle from where it didn't come from, but I need to know now. Otherwise, there may not be a tomorrow.
Wesson, where are you?
About a quarter mile from ground zero.
I think this is about as far as we go. Our feet are sizzling. And I'm getting rammed to nearly the limit of our gear.
Okay, cut the rover loose and get the hell out of there.
Roger that.
Dylan, the crate the bomb was shipped in. Somebody had to sign for it when it got to port. Customs must have a database. Get me a name. And where's Kevin?
No, we don't. We're checking the hospitals.
Have you tried Memorial?
You wouldn't be there. It's on the other side of
No, I mean, is it still... It's Kathy's hospital.
As far as I know, it's still there, but the phones are down. So.
All right, can you keep checking for me? Thanks. Look, John Clark was in Haifa yesterday. I don't know where he is today, but he may have something, so we have to find him right away.
Wow, check out that gadolinium reading.
Yeah, the mass fraction is huge. Okay, connect me to Dylan, will you? I'll hold.
There it is. Savannah River.
Oh, yeah. Oh, yeah, what?
They always have that gadolinium problem. Hanford does it another way. They always generate too much promethium.
Hold on a second. Can you translate that into English for me?
This plutonium came from the DOE plant at Savannah River, February of '68, from K reactor. You can even tell which part of K reactor.
Wait a minute, this is our plutonium?
Made in the USA.
Dylan, you gotta find Cabbage for me.
So hopefully you were able to think of some of the questions and see the questions that came to mind during the movie that will be of paramount interest during a post-detonation recovery operation. So some of the things to be concerned about are, what are the prompt effects from the detonation, about damage and death that interfere with or compete with the resources for doing forensics. You have to be able to know the cloud rise and transport of the fallout. Of course, they're going to want to know, where is the president during this time. First question people ask is, who did it, right? I need proof. That's what technical nuclear forensics is. And of course, you got to be able to communicate that truth, technical people, to the intel or the policy people. There's a lot of time pressure involved because you have to get the answer yesterday. There will be a command post. There will be some radiological assessment teams. You might have to be in tunnels or south of the city, or definitely outside the radiation area. What direction are the winds blowing? You have to do the collection. You have to analyze and report it. But of course, the timelines shown in the movie are for getting the movie done in 90 minutes, as most Hollywood movies are. The fact that they almost are collecting fallout right after it falls on the ground is pretty unrealistic. They went in a quarter mile from ground zero, the collectors did. I don't know what they were talking about. It was sizzling and at the limit of their gear, because their gear doesn't really stop gamma radiation, as you're probably aware of. The robot collections were taking place, although the collectors, the manned collectors, were right there. They probably should have just scooped it up themselves if they were already in that location, already getting the dose. They did some field analysis. Of course, they talk about a gadolinium mass fraction, right? So there's some sort of elemental, but there's also isotopic analysis that would be done. And they look up a nuclear forensics library, right? Like they have it handy in this little notebook of theirs that they carry around. And they can tell you it came from the Savannah River K reactor, which part of the reactor it came from, and when, the date stamped it. All of these things are conceivable, but in the timeline, in the pressures, and in the way that it was shown are probably unrealistic. So we're going to walk through post-detonation nuclear forensics in this sort of circle diagram. We're going to start with prompt diagnostics. We're going to go to debris collection. We're going to talk about field analysis and data evaluation. And along the way, we're going to show some of the work being done at Oak Ridge in these 4 areas. And at the bottom of this figure, you can see some of the students that have worked with us since 2008 over the summers to help with this post-detonation nuclear forensics modeling and simulation research. So the first area, that first quadrant that we're going to talk about, is prompt diagnostics. Of course, when we tested our own weapons, we had diagnostics going on during the test. That's basically to see how well did your design perform. So that's when it's your own device. When it's an unknown device and you're trying to determine how well it performed, that's also part of nuclear forensics, post-det nuclear forensics. So let me show another video here.
To learn more about the atom bomb, we divide our testing into 2 major areas: diagnostic testing and effects testing. More specifically, diagnostic tests are an extensive examination of the phenomena occurring during the initial phases of the explosion. Effects tests study the external manifestations of the explosion, the effects of the weapon. To gain an intimate understanding of interior weapon behavior, 3 kinds of diagnostic measurements are made. These are the time it takes to start the nuclear reaction, transit time; the rate at which the chain reaction multiplies, alpha measurement; and measurements of the total energy released in the nuclear reaction, yield.
So of those 3, yield is the primary one that we're after. And that's because almost everybody in the community needs to know what was the yield of the event. For the event in the Sum of All Fears movie, I think they say somewhere in the movie that it was 8 kilotons. Again, that's less than half of the first generation weapons that we put off, a little boy and Fat Man. So 8 kilotons is a massive yield. Of course, they targeted Baltimore Ravens Stadium, if you remember in the book, which is great because I'm a Patriots fan. So we want to see the Ravens go down. Anyways, the yield is needed by consequence management, by the effects community, for forensics as well. So one of the research areas we did at Oak Ridge was look at how could we use the observed cloud top, shown here on the right of the lower figure, is a picture of the cloud rise. When it comes to stabilization, that height that which it attains is directly proportional to the yield that was released, or not proportional, but related, and that we could use our cloud rise models to try and predict iteratively what yield best matched that observed cloud top. And so on the right, I have some simulations that we did with our cloud rise model for one, a historic shot at Nevada test site, and also a modern scenario in New York City. Let me see if I can get this to work. This has no video. So this is Buster Jangles Sugar. It's a 1.2 kiloton detonation in Area 3 at the Nevada test site. And this is just a short KMZ animation of what the size and growth and advection or drifting of the cloud during cloud rise during its first 5 minutes would obtain. Now this is a 10 kiloton national planning scenario number 1 for the U.S. is a 10 kiloton shot, surface shot, and these are non-responsive buildings downtown Manhattan. I detonated a 10 kiloton device, and this is how high the cloud would go. Of course, it would be slightly different due to the urban interactions, but you can barely see it, but there's a shadow of this cloud as it moves north along the Manhattan Island and eventually go up to Albany and RPI, where my alma mater is, and leave fallout up there. But you can see that if you know how high the cloud goes, that was directly proportional to the yield if you have trust in your models for cloud rise. So one of the other things that happens during that prompt phase in that first quadrant of that circle I'm going to use as an outline is the debris formation. So this fallout, basically everything gets vaporized, all the soil gets lofted, and the fission products and the actinides start to condense onto that soil as the cloud starts to cool. So shown here is the cloud temperature as a function of time in the early seconds after detonation. As the cloud comes down from millions of degrees and it passes through at about 2 seconds, the 3000 Kelvin mark, and keeps coming down to the 2000 Kelvin mark. At 2000 Kelvin, silicon dioxide wants to solidify. So things that can condense before 2000, higher temperatures than 2000 Kelvin, will be distributed throughout the volume of the molten soil particles, silicon dioxide particles. Once those silicon dioxide particles freeze at 2000 degrees Kelvin, the remaining elements will have to condense on the surface of the particle. This causes a distortion or a fractionation of the elements within the particle. And of course, these elements are highly radioactive. They're changing by beta decay and therefore transforming from one element to another during these few seconds. So this schematic tries to show that changing of the elementals due to the radioactive beta decay of the primary fission products. So most fission products are born neutron rich, or on the neutron heavy side of the line of stability, and they get stable by turning neutrons into protons and emitting beta particles. As they go to the line of stability, they're changing elements. So the same mass is kept, but a neutron is turned into a proton, which means it changes element but keeps the same mass. So sometimes these are called mass chains. So the mass chains shown here are 3 different ones, and they have either a V for volatile behavior for that element or an R for refractory behavior for that element. Again, refractories can condense at high temperatures and will be volume distributed within the molten particle, and the volatiles have low condensing temperatures and therefore will be coating the outside of a frozen soil particle. And so you can see for mass chain 89, all the elements in this mass chain are volatile. So it doesn't matter where the atoms are when the particles solidify at about 2.5 seconds, I think, for this case, because they're primarily these 2 elements. The starred elements, isotopes, are the primary fission products for that mass chain. Within a mass chain, when they're first born, things are Gaussian shaped around some most probable Z. So you can see most of the material is formed as krypton and bromine, and at 2.5 seconds, it really hasn't decayed a whole lot. So they're all volatile, and this will all have to be coated on the outside of the particle. For mass chain 95, A equals 95, you have all refractories at the time of particle formation, the 2 starred ones. So again, this one would be all volume distributed. But some mass chains are mixed, like the 141 mass chain, where it's born partly as cesium and partly as barium. Cesium is volatile and cannot condense, whereas barium can. So the barium will be volume distributed, but the cesium will have to wait till it decays and cool, and therefore will be coated on the outside. Now, eventually, these all take time for you to collect the sample, bring it back to the laboratory, and analyze it. And the gray shaded boxes at the end show you which isotope you're going to end up analyzing in the laboratory, because it takes you minutes to hours to get the sample from the fallout field to the laboratory analysis. So you might be analyzing strontium-89 because of its 50-day half-life in the laboratory. But when it was formed as a particle, it was bromine and krypton. So that's just something to keep in mind. So to give a more formal definition of fractionation, I use Freeling's article in 1961. Freeling says that any alteration of the radionuclide composition between detonation and sample analysis is termed fractionation. Now, there are 2 types of fractionation. There's radiochemical fractionation, as we just discussed in the previous slide. As things decay, and they're either refractory or volatile elements, and it's actually perhaps those oxides of those elements, you have to know what species is it going to form, what is the condensation temperature of that species, and how will it condense, at what temperature and at what time. Now, after it's formed onto particles, we find there's also a physical fractionation, or a separation of the physical particle sizes that occurs that also contributes to fractionation. That physical fractionation is that the early forming particles, which are, remember, primarily refractories because they condense early, they grow to be larger in size and fall out closer into ground zero. The later forming particles, those volatiles, they can condense, but they can only condense on material particles that are still in the cloud when they reach their condensation temperature. So they tend to favor smaller particles and therefore stay aloft longer and blow downwind further. Therefore, you're more volatile downwind in the fallout field. So this fractionation, both chemical and physical, creates this distortion so that you don't get the same radionuclide inventory everywhere on the ground. Close into ground zero, you get a more refractory dominant radionuclide inventory, and downwind, you get a more volatile dominant radionuclide inventory. So some of these radiation properties are a fractionated fallout can be seen when you start looking at the differences between a refractory sample in the top left and a volatile sample in the bottom left. And I apologize if you can't see these. Hopefully these slides will be distributed to you. But you can see that some of these nuclide growth and decay curves for each specific isotope, the amount or the relative percent of the activity for that isotope changes based on the fractionation level. Refractory at the top, volatile at the bottom. So take a closer look at these when you get a chance and you'll see that difference. On the right-hand side, what we're trying to show is in the top right, the gamma spectra. This is the emission of gammas, and it's coarsely binned into 40 groups over 4 MeV. And you can see that the fractionation has distorted the relative amount of gammas given off in each of the bins, primarily because of isotope abundances going up and down that contribute to that bin. And in the lower right, we have the dose rate, and you can see the variability of the dose rate dependent on the fractionation level. So you can't have one model that gives you one answer for everywhere in the fallout field, either for isotopics, gamma spectra, or dose rate, because it's going to change depending on where you are in the fallout field. So that's prompt diagnostics. Let's move on now to debris collection. So Oak Ridge has supported debris collection by providing mission planning tools, fallout prediction of concentrations, and dose rates. So debris collection. How is debris collected historically? Well, in the very first test in 1945, we had Trinity. And Trinity was an experiment, right? It was going to be taken in Alamogordo, New Mexico, and detonated there. Again, a first-generation weapon, around 20 kilotons yield. And they were trying to figure out, how are we going to do diagnostics on it to figure out how well it performed? So Enrico Fermi, decided we should go in and collect samples of the fallout to do radiochemistry and determine how well the device performed. They knew what they put in the device. By collecting the debris, they could see how efficient the device was and what the yield was by how many of the fissile atoms fissioned. So they decided they lined a bunch of two tanks with lead, and they were going to drive these tanks in. Fermi was in one, and his postdoc was in the other. And Fermi's tank broke down. So the postdoc was the only tank that went in, and it was rigged with scoops, and they picked up fallout, brought it back to Los Alamos, and analyzed it and did diagnostics on the weapon. So from the very first test, we've been doing ground sampling to do forensics, post-det forensics, on how well a device or what type of device performance occurred. So what I have here are 3 videos of other ground sampling that occurred both at Nevada and in the Pacific.
To make this possible, Army weasels, drone weasels, are warming up now for a sample collecting trip into the crater area. Sample gathering by remote control, observed and accomplished through the use of television. Mounted on the front of the weasels are compact television cameras that can be made to move in any direction, like the weasels themselves. One of the drones is fitted with scoops on the front, which will, hopefully, return filled with Earth samples from the crater area. They travel their own private road from the remote control station to the mound of Earth that circles the surface-shot crater. The other weasel has a drill bit mounted on the back, which will be doing some remote-controlled digging for sample cores of the crater.
So as you see, that's not unlike the Tom Clancy clip where they had a robot at a quarter mile from ground zero trying to do scoops. These robots went right to the lip of the craters of the Buster Jangle shots.
Secondary objectives of the underground shot were to obtain additional data on fallout and residual radiation, base surge, ground shock and air blast, and earth shock loading. Studies of radiation on this shot were especially significant because of the immense amounts of soil that would be contaminated and dispersed over the surrounding terrain, both from the base surge and fallout. Collectors and samplers, badges and dosimeters were set out before the burst at locations predetermined by the wind forecast. Those in hot areas were set out on trailers attached to long lengths of cable so they could be hauled out safely. The objective was to determine the distribution and intensity of fallout and to plot isodose rate contours on the radiation field as a factor of time.
So that's an example of what they called an incremental fallout collector. Again, they were pre-placed. They knew where the detonation was going to happen. They knew which way they wanted the wind to go, so they were put in the direction of the fallout field. We don't have that luxury today. We're going to go in where there aren't any pre-placed samplers and have to collect samples. There were some other difficulties in the Pacific for those shots, as you might imagine, and here's some video clips from the Pacific shots.
To study the physical, chemical, and radiochemical nature of fallout after it reaches the surface, a number of collection techniques were used. Land stations located throughout the atoll consisted of total and time incremental collection devices for the purpose of gathering gross samples as well as samples versus time, from which time of arrival, rate of fallout, and time of cessation could be established. Since available land areas were covered by only a small fraction of the total fallout pattern, an array of floating instrument stations was moored within the lagoon and at sea to the north of the atoll. 3 pontoon rafts, instrumented to measure time of arrival, total exposure, and to collect total fallout samples, were moored in the lagoon. In addition, 2 YFNB barges with total and time incremental samplers and a variety of other instrumentation were moored inside the lagoon. In the ocean to the north of the atoll, some 16 skiffs were moored to collect total fallout samples, measure integrated exposure, time of arrival, and penetration of activity to various ocean depths.
So what if the detonation took place in Baltimore and the winds went straight east, westerly winds that they call them, or New York City or Boston and the winds went straight east? You'd have very few places to collect ground samples. You'd have to resort to water-based sampling. So there are some concerns with some of the top threat scenarios for both ground and water sampling. So mission planning, the fallout's down on the ground. You have to send that radiological assessment team in to do the collection, or in our case, they call it the Ground Collections Task Force. It's an interagency, FBI-led, DOD are the collectors, and DOE analyzes the fallout samples in the field. It's a 3-agency team that deploys after an event. They're on pagers, they're on watch, they have to go rendezvous and then get shipped out to the site of the event to set up a base of operations and do mission planning. Now, the mission planning is, their goal is to collect samples which are quality samples while also calculating dose to the collector. They don't want to send the collector in and them basically be walking dead when they come back, but they also want to make sure that if they're going to send someone into the radiation field, that they come back with a quality sample. So what is a quality sample? Quality sample has a certain amount of mass of sample, so the area has to have a certain amount of mass per unit area for them to collect. It has to have a certain amount of activity in it so that the radiochemist has enough material to actually detect with the radiation detection equipment. And it has to have varying degrees of fractionation. Remember we talked fractionation changes with location on the ground or in the air as well if it stays airborne. You need various amounts of fractionation so that you can back correct or do the inverse problem to the unfractionated point. So fallout prediction, here's a historic video on how they used to do fallout prediction. And on the right is shown the command mission planning tent where they do fallout prediction real time in the field.
In the first few minutes, the visible cloud will reach from 60 to 100,000 feet or more for multi-megaton bursts with a stem over 5 miles in diameter. Fallout of the radioactive particles inside and below the visible structure now begins through the operation of gravity, rainout, convection, and other mechanisms. The active airborne particles move on downwind, causing significant fallout for a period of 10 hours or more. The settling dust reaches ground in a pattern which, while naturally quite variable, is reasonably represented as a long leaf shape. Starting back at the time of burst again, it is important to note that while the visible cloud will move with cloud height winds, the fallout particles will settle through lower winds of possibly conflicting directions at various heights. Orientation of the ground fallout pattern is determined by a resultant wind vector which is an average of all winds from ground to cloud height. Therefore, the fallout pattern may take an entirely different path from that of the visible cloud. Changes in the average wind vector as the falling dust moves across country can cause major distortion of the fallout pattern.
So again, that was for a multi-megaton weapon. For a kiloton range weapon, we're talking about 15 to 25,000 feet. So it stays in the troposphere. It will come down with weather. It doesn't go into the stratosphere and become global fallout. It becomes local to intermediate fallout. So how do you predict fallout today? Well, at Oak Ridge, we have this code called DELFIC. DELFIC is the Defense Land Fallout Interpretive Code. And basically, you give it inputs in yellow, shown on this flow chart. It creates these intermediate results in gray. It uses the libraries, both nuclear and thermodynamic libraries and fractionation correlation libraries, to produce the final results of the distributed fallout on the ground. It basically is constructed by 4 main modules: an initial conditions and cloud rise module, the atmospheric transport module, the particle activity model, which basically does the fractionation predictions, the radionuclide buildup and decay, and then the output processor module, which converts the grounded fallout into values of interest, dose rate as a function of time and location, time of arrival of fallout, time of cessation of fallout, rate of arrival of fallout, mass of fallout per unit area, activity per unit area. All the things that we talked about on previous slides, the DELFIC model predicts. That's why Oak Ridge chose the DELFIC model to supply to this ground collection task force for doing their mission planning. So again, DELFIC is the Defense Land Fallout Interpretive Code. It's a historic Defense Threat Reduction Agency code developed by DTRA's predecessor, the Defense Nuclear Agency. What we provided here at Oak Ridge is the fallout planning tool developed by Ron Lee to go out and provide Google Maps and Google Earths and a fancy user interface for the mission planners to actually interact with the predictions of this physics tool, DELFIC. Again, it's used today. It's been used since 2009 continuously for the deployable ground collections task force for doing their mission planning. So what I show here is the sum of all fears scenario. So it's a Baltimore detonation on the Ravens Stadium where the president was, I guess, attending the football game. And what you can show is after you do the DELFIC prediction and you plot it on Google Maps, you can plan a route through the fallout field as shown here by the green radiation symbols and the red plus signs. So the radiation symbols are places where the collection team might stop and pick up a scoop of dirt or vacuum up or sweep up some dirt fallout and bring it back for analysis. And if you mouse over with this tool over any one of those collection points, in this case I'm mousing over the southernmost point, you can get any of the values that DELFIC predicts for that location presented to you. So in this case, it has the dose rate in R per hour at 1 hour, the dose rate at 24 hours if they were to go in at 24 hours after the event. And in this case, it's about 4.5 R per hour, 24 hours after the event. So that might not be acceptable to some people, but for life-saving and forensics and other issues, that might be an acceptable dose rate to go into. It also tells you how many equivalent fissions per unit area, square meter, are at that location. So at that location, there's 10 to the 16th fissions per square meter. So fissions is a term of activity that is time invariant. The number of fissions don't change, just the activity changes with time. So at that location, I have 10 to the 16th fissions per square meter. If I pick up 1/100th of that, or 10 to the 14th fissions, and a kiloton is equivalent to 1.45 times 10 to the 23rd fissions, you basically have a nano bomb. So you've got a nano fraction of the bomb if you pick up like an HP swipe 100% efficiently of that location and bring that back for analysis. So that's a sufficient amount of activity to do your radiochemistry on. So all you need is a nanofraction of the bomb. You don't need to sweep up the whole field and bring it back. You don't need that much activity. And of course, other things they might be interested in shown here is the particle size. What is the largest particle size I expect to see at that location? And here it's just under a millimeter, or 900 and something microns. So that is visible by the human eye. I mean, you can see particles down to about 50 microns. Then you need instruments to see them below that. So a millimeter sized particles are like table salt. You can definitely see that. So again, this is showing the same result in Google Earth. And again, the detonation took place at the stadium. They set up their base of operations just south of the city in the tunnels along the harbor. And of course, you would want to somehow go around the blast damage zone, shown by the concentric rings, red being severe damage where everything is down. That's where they were at the quarter-mile mark, right? Then there's moderate damage in yellow and light damage in purple. Now, the light damage is basically a half a PSI, where you might get window breakage, but walls and buildings are still standing. So a lot of life-saving is going on in those blast damage or prompt damage zones. So that's why I put a route north of the city, outside the damage zones, where you still got sufficient activity, mass, and dose rates that were bearable 24 hours after the event. So you don't have to go to ground zero, is my point, in collecting ground samples. Now, shown as an inset here is a tablet screenshot. So what Ron has done is, in a modern fallout prediction with DELFIC, he has made the ability to run this on your smartphone or your smart tablet, run the DELFIC inputs, send it off to the server. The server does the calculations and sends the results back to your phone or your tablet, so that you can use the GPS in your phone or your tablet to tell you what the expected dose rates are as you walk through the fallout field. Very slick, very ingenious work being done here at Oak Ridge. So next, I want to talk about is debris collection, but this time from airborne sampling. What if you don't have access to the site? What if it goes over the water and you want to try and somehow sample the cloud like we did back in the Nevada test time and the Pacific as well? Shown on the right is the sampling chronology. You would send these jets or sometimes bomber aircraft through this three-dimensional cloud with filters on the wings, collect the fallout, land the plane, have a guy with a literal 10-foot pole take the filter paper off the plane and have that shipped back to a fixed laboratory, at the time Los Alamos or Livermore, to do radiochemistry analysis of the filters to determine the efficiency or the diagnostics of the bomb. And on the left, I have a short video clip showing how that was done.
The biography of every atomic cloud is essentially the same. The intense heat and violence of the fireball as it sears the sky causes the spectacular and colorful rust-like condition in the air around it. As the fireball cools, an enormous vacuum and afterwind is created, causing the desert floor to rise up into the cloud itself to form the characteristic mushroom stem. The cooling also sets up a rapid condensation in the air around the fireball that sometimes produces layers of ice crystals, literally an ice cap. Knowledge gained on previous nuclear weapons tests has produced the theory that once the cloud has formed and stabilized in the sky, the vitally significant fission products in so-called unburned fission fragments don't distribute themselves evenly, but tend to collect in very large, invisible pockets, hot pockets, or cells inside the cloud. The particles that are suspended in these nebulous cells indicate many things that happen inside the bomb, as well as the efficiency of the fission reaction. So attempting to locate the cells and collect samples from them is a mission of the highest priority. Visually, Cream Puff 3 seeks out and heads for the most dense portion of the cloud. His mission plan is simple. Before reaching the visible cloud, the sensitive survey meters in the plane start to climb as it enters the invisible field of gamma radiation that surrounds the cloud. If the plane misses a cell, the meters return to almost a zero reading when it emerges from the gamma field on the opposite side. If so much as the edge of a cell is touched, the plane is instantly contaminated, and the meters will continue to read comparatively high. The plane will continue to make passes until it has made a sufficient number to collect the required sample.
One means of measuring yield is to attach filter traps to drone aircraft and send them into the core of the atomic cloud immediately after the blast. Nuclear ashes or samples of the residue material saturating the cloud are collected in the traps for radiochemical analysis to determine the total number of fissions that have occurred.
So as I was talking about earlier with the ground sample collection, you want to have a certain amount of fissions in your sample so the radiochemist can do his analysis. So we've talked about prompt, we've talked about debris collection. Let's talk about the field analysis that's done after the samples are brought back. And I'll go quickly through these last two quadrants, but field analysis, basically, they bring the samples back, they put it in a secure sample storage site, a lead-lined container, waiting for it to go through the remaining stations. The sample might be a dirt sample with fallout mixed with it. Remember, they don't have pre-placed collection sites, so they're picking up this fallout with other dirt in the background. So they might want to sieve the sample to separate the radioactive particles that are primarily melted, larger particles perhaps, from the finer dust that may have been vacuumed up or swept up when they did the collection. Once they have that size separated sample, they bring it to what they call a high-grade tent, where they do an initial assay of the sample. Using a sodium iodide detector, they determine the number of fissions on that sample. If it has enough fissions, it's determined to be a potential quality sample and moved on to a triage tent. In the triage tent, they collect the gamma spectra to determine the isotope ratios, which will help them, and I'll discuss this on the next slide, determine the degree of fractionation. Was it refractory from close in at ground zero, or was it more volatile as we move further away? Shown in the top right is the triage detector being used, some of the radionuclide buildup and decay, and the fractionated fallout field in the bottom right. Once you determine the degree of fractionation and it has a sufficient number of fissions in it, and the mass or specific activity is high enough, and they consider it a quality sample, well then the FBI will ship that sample to a fixed lab with a dedicated aircraft to get those samples going in a fixed laboratory analysis. So the triage step, let's look at that in more detail. What you want to do is you want to collect a gamma spectra, which is of course changing with time because radionuclides are growing in and decaying away. So what they try and do to determine the degree of fractionation is they take the ratio of 7 photopeaks of 5 different isotopes and they build 4 different ratios. And that's just for robustness or redundancy. They really just need one good ratio of 2 photopeaks from 2 isotopes to determine the volatile refractory nature of that sample. And once they determine the degree of fractionation, if that is unique and or if it's a degree they want, along with the number of fissions, it's determined shippable back to a fixed lab. So some of the research we're doing here at Oak Ridge includes if we were able to exploit some pre-existing systems that are out there in the country that would be collecting gamma spectra already. One of those systems is the EPA's RadNet sodium iodide network. That network is set up for air quality. EPA is checking air quality at all the indicated sites on a map of the continental United States. Every radiation symbol is a population center, and they typically have one of these sites. This is a photo of the Knoxville site we went to visit, and unfortunately it's sodium iodide. So how well can we determine forensically information out of that spectra? So we did some modeling and simulation of this system. We did the fallout prediction for a 10 kiloton detonation in Washington, D.C. We looked at what would the sodium iodide spectra be from our EPA RadNet system that might get hit with fallout. And then we said, well, what if we swapped it out with a high purity germanium detection set? So that's some interesting research that's just concluding. In doing that research, we discovered that some of these photopeaks might be distinguishing and have forensic information in them, but we weren't quite sure if that was just an artifact of the nuclear data uncertainties that propagated through all the way to the gamma spectra. So basically, you have nuclear data uncertainties in the fission product yields, in the half-lives, in the decay modes, in the gamma line intensities. Each of those contributes to the ultimate photopeak that you're measuring in your triage gamma spectrum. So that you want to know how much of that, what's the uncertainty in the photopeak of both the numerator and the denominator of the ratio you're creating, so that you can determine what the uncertainty in the ratio is, so that you know how well you can trust the R value that you predict, the refractory or volatile nature that you're predicting of that sample. So that's field analysis. Let's conclude now with our data evaluation. In data evaluation, it's just like we did with diagnostics back in the underground testing. You had a design of a nuclear test, you detonated it underground, you drilled underground to where the detonation took place, you took a sample, you did a high grade, you did the dissolution, you did the radiochemistry, you did elemental analysis, you did isotopic analysis, you did mass spec, maybe alpha, beta, and gamma measurements, and then you sent all that data to a data analysis and interpretation individual, or what they call a debris diagnostician. This is the same thing we're going to do today in an above-ground terrorist event with forensics as our focus, since it's not one of our own devices. So fallout data evaluation is trying to basically take cloud samples which are termed volatile and ground samples which might be refractory, and see the spread in this line in the top right figure. We're going to try and bring back to the 0.11 to determine what is the isotopic mix and the unfractionated point. And this is just one step in the debris diagnostician's duties. And why do we do that? We do that because we can determine fission type based on the fission product ratios. So as you can see here, we're showing basically the fission product yields for 3 different materials, all with the same neutron spectrum. And you can see they're different for some isotopes, and they're exactly the same for others. So if you take the ratio of one that's different to one that's the same, you can see and potentially determine which fissile isotope got fissioned. Similarly, if you change the neutron energy, these curves change, and you can also potentially get what the neutron spectrum was. So a combination of knowing the fissile material and the neutron spectrum, you should be able to tell whether it was a little boy or a fat man that was detonated. So that's a data evaluation in 2 slides. So again, we've talked about many different things. We talked about prompt diagnostics, debris collection, field analysis, and data evaluation. We motivated it with some of the historic videos of how this was done during our atmospheric test experience, as well as the modern scenario from Sum of All Fears. And I hope this generates questions for our question and answer session in April. Thank you.